Tonight, we are going to spend the night with the last planet. Out past Jupiter, past Saturn, past pale sideways Uranus, at the far cold edge of the Sun's family, there is a world of deep blue where something is happening that should not be possible. The strongest winds in the solar system do not blow on Jupiter with its huge churning storms. They do not blow on Saturn. They blow on Neptune, a planet so far from the Sun that high noon there is dimmer than twilight here, a planet that receives 900 times less sunlight than the ground you are lying on right now. By everything we thought we understood about weather, Neptune should be the stillest place in the solar system, a frozen, sluggish, sleeping world, too starved of energy to stir. Instead, its winds scream past 1,200 miles per hour, faster than the speed of sound as we measure it here on Earth, faster than any hurricane, any tornado, any gust ever recorded on any other world circling our star. You may have heard that Neptune is cold and far away and blue. That much is true. But here is the thing most people don't realize. Neptune is not a quiet outpost at the edge of things. It is the most violent weather engine the Sun owns, burning with a hidden inner heat that nobody has fully explained, on a world that has been visited exactly once, for a few hours, decades ago, and never again. Tonight, the dim blue point at the edge of the solar system is going to become a place, and by the time we are done, the quietest looking planet in the sky will never look quiet to you again. Now, let's begin. Before we go far, settle in. Let the blankets get heavy, let your shoulders come down from your ears, and let your breathing slow to whatever pace it wants. Maybe the lights have been off for a while already. Maybe you are on a night shift somewhere quiet, or lying awake listening to a house that has gone still around you. Wherever tonight finds you, you are in the right place. And there is nothing you need to do here. There is no test at the end. If you drift off somewhere over the cloud tops of Neptune, that is not a failure. That is the point. The planet will keep spinning whether we are watching or not. It has had a great deal of practice at that, as you are about to hear. Let us start with the part that should not add up, because it is the heart of everything tonight. Neptune orbits the Sun at a distance of about 2.8 billion miles. That number slides off the mind, so hold it against something familiar. Earth sits about 93 million miles from the Sun, a distance astronomers use as their basic yardstick. Neptune is 30 of those yardsticks out, 30 times farther from the fire than we are, and the light of a fire does not fade gently with distance. It fades with the square of the distance, which means 30 times farther away works out to roughly 900 times less light and 900 times less warmth falling on every square foot of the world. 900 times. Stand outside on a bright summer day at noon, and the world around you is almost too bright to look at. Now dim that day 900 times over. What is left is something like the last blue light after sunset, that deep dusk where you can still see shapes, but the color has drained out of everything. That is noon on Neptune. That is the planet's best moment, its brightest hour, the most energy the sun ever gives it. The sunlight that does arrive there is so tired that it takes over 4 hours just to make the trip, racing the whole way at the fastest speed the universe allows. When a ray of sunlight finally reaches Neptune's cloud tops, the Earth it passed near the beginning of its journey has already turned a sixth of the way around. A world on that kind of starvation diet should be simple. Cold, yes. And Neptune is cold, with cloud tops near -200 degrees Celsius. But more than cold, it should be still. Weather, everywhere we understand it, is a machine that runs on sunlight. On Earth, the sun heats the tropics more than the poles. Warm air rises and cold air slides in beneath it. And out of that endless unbalancing comes every breeze, every front, every storm that has ever rattled a window. Starve the machine, and it should slow down. Give a planet almost no fuel, and its atmosphere should barely creep. And yet, point a telescope at Neptune, clock the clouds as they race around the planet, and you find air moving at speeds that no place on Earth has ever touched. The strongest hurricanes our planet has ever produced top out a little above 200 miles per hour. And we name them, and we remember them for generations, and we rebuild for years after they pass. Neptune's ordinary winds run 6 times faster than that. Measurements from the one spacecraft that ever visited clocked winds past 1,200 miles per hour near its great storms, and some estimates push the fastest jets higher still, up toward 1,500. On Earth, sound itself moves at about 760 miles per hour at sea level. Neptune's winds outrun that figure with room to spare. If you could stand at the cloud tops, which you cannot, the air would not howl past you. It would arrive faster than the sound of its own coming. So the planet with the least sunlight has the fastest wind. The world that should be the stillest is the wildest. And that is only half of the mystery, because when scientists finally got close enough to take Neptune's temperature properly, they found something stranger than the wind. Neptune is warm, not warm the way a summer day is warm, but warm in the accounting, warm in the books. Measure carefully how much energy falls on Neptune from the sun, then measure how much energy Neptune pours back out into space as heat, and the two numbers should more or less match, the way they roughly do for Earth. They do not match. Neptune radiates about 2.6 times more energy than it receives. For every unit of warmth the sun sends it, Neptune gives back more than 2.5. Think about what that means for a moment. More than half of everything Neptune spends, it spends from savings. There is a furnace inside that planet, some deep, private reserve of heat left over from its birth or generated in ways we are still guessing at, leaking steadily up through the clouds and out into the dark. And it is that hidden furnace, most scientists believe, that stirs the atmosphere into its impossible fury. The sun does not drive Neptune's weather. Neptune drives Neptune's weather. The last planet is not a frozen ornament hanging at the edge of the system. It is a world with its own fire in its belly, running its own engine, ignoring in some deep sense the star it belongs to. And here is the detail that turns a puzzle into a genuine mystery. The detail we will keep circling back to tonight the way scientists have circled it for decades. Neptune has a twin. One planet in, there is Uranus, and, by every obvious measure, the two of them are siblings. Nearly the same size, nearly the same weight. Built, as far as we can tell, from nearly the same recipe of rock and ice and hydrogen, wrapped in atmospheres tinted by the same methane. Two peas from the same cold pod at the far end of the solar system. But when you take Uranus's temperature the way we took Neptune's, the furnace is not there. Uranus radiates barely more energy than it receives, so close to break even that its inner fire, if it has one at all, is a candle next to Neptune's bonfire. One twin burns from within. The other is cold all the way through or close enough. Same size, same recipe, same neighborhood, and two utterly different fates, and nobody can yet tell you exactly why. Whatever answer you reach for, you have to explain both worlds at once, and every simple story fails on one twin or the other. Hold that question tonight. It is one of the outstanding unsolved problems in planetary science, hiding in plain sight behind the two dimmest planets in the sky. But before we go down into the storms and the furnace, we should meet this world properly, and Neptune's introduction to humanity is unlike any other planet's, because Neptune is the only planet that was found with a pen. Every other world we knew before, it announced itself to the eye first. Mercury, Venus, Mars, Jupiter, and Saturn are bright wanderers that every ancient culture watched cross the night sky, planets before anyone knew what a planet was. Uranus was spotted through a telescope in 1781 by the astronomer William Herschel, who at first suspected he had found a comet, and only slowly realized he had doubled the size of the known solar system. But Neptune was never spotted. Neptune was deduced. Neptune was predicted into existence by arithmetic, the way you might solve for a number you cannot see from the numbers you can, and the story of how that happened is one of the great detective stories in the history of science. It begins with Uranus misbehaving. In the decades after Herschel found it, astronomers did what astronomers do with a new planet. They charted its path, applied the laws of gravity that Isaac Newton had given them, and computed exactly where Uranus ought to be on any future night. Tables were published, predictions were made, and year after year, Uranus quietly refused to obey them. It was never far off, only a whisker, a discrepancy so small you could hide it behind a human hair held at arm's length against the sky. But the whisker would not go away, and it grew, and it had a shape. Sometimes Uranus ran a little ahead of where the mathematics said it should be, as though something out in the dark were pulling it forward. Later, it lagged a little behind, as though the same unseen hand had swung around and was now holding it back. To most people, an error That small would be nothing, a rounding mistake, a smudge on a lens. But to the astronomers of the early 1800s, it was maddening, because Newton's gravity was the most precise and most trusted idea humanity had ever possessed, and either the great law was subtly wrong, or something enormous and invisible was out there, tugging on the outermost planet from the darkness beyond it. In Paris, a mathematician named Urbain Le Verrier decided to find out which. What he did next sounds almost impossible when you say it plainly. He sat at a desk with paper and ink and the misbehavior of Uranus written out as columns of numbers, and he worked the problem backward. Instead of asking where a known planet would go, he asked what unknown planet would have to exist, how heavy, how far out, and where along its orbit it would have to be standing right now to bend Uranus's path in exactly the ways the observations showed. It was a monstrous calculation, months upon months of hand computation, every step done with nothing but a mind and a pen, solving for a world sight unseen. In the summer of 1846, he had his answer. A predicted position for a planet nobody had ever knowingly laid eyes on, and at the end of August that year, he presented it to the French Academy of Sciences. The astronomers of Paris did not rush to their telescopes, so Le Verrier did something slightly desperate. He wrote a letter to a young astronomer at the Berlin Observatory, a man named Johann Galle, and asked him, more or less, to please point his telescope at a particular patch of sky between the constellations Capricorn and Aquarius and look. The letter took 5 days to reach Berlin, arriving on the 23rd of September 1846. Galle asked the observatory's director for permission to search that very night, and he was joined by a student named Heinrich de Rest, and this is the part of the story I want you to slow down and actually picture, because it is one of the quietest, enormous moments in human history. A dome in Berlin, after dark. 2 men, one at the eyepiece of the great refractor, calling out the positions of stars one by one, the other hunched over a freshly printed star chart by lamplight, checking each called position against the map. Star on the chart, star on the chart. And then, not long after they began, less than an hour into the search, Galle read out a faint point of light, and from the desk de Rest said the words that ended one era of astronomy and began another. That star is not on the map. They had it. It was sitting less than 1 degree from the spot Le Verrier's pen had marked, about the width of your little finger held out against the sky. They watched it the following nights, saw it creep against the background stars exactly as a distant planet should, and the thing was done. A man in Paris had aimed a column of arithmetic at the heavens, and a man in Berlin had looked along it and found a world. I want you to sit with how strange and how wonderful that is. Neptune is invisible. In all of human history, no unaided eye has ever seen it. It is the only major planet that simply cannot be seen without help, drowned out by distance, 100 times too faint for the sharpest night vision on the darkest mountaintop on Earth. for all the tens of thousands of years that people have watched the sky, through every civilization that named the bright wanderers and built calendars and temples around them, Neptune circled silently beyond the edge of sight, unsuspected, unimagined. And when it finally entered human knowledge, it did not come through the eye at all. It came through the mind, a trembling in the path of one planet, read correctly, betrayed the existence of another. Gravity itself was the messenger. The heavens, it turned out, could be read like a ledger, and a missing entry could be worked out from the way the other numbers leaned. Neptune was the proof, the demonstration to the whole world that the universe runs on laws so exact that a human being with a pen can reach across 2 billion miles of darkness and put a finger on something no one has ever seen. There is a small, humbling footnote to this triumph, and it is worth telling because it shows how close the story came to being completely different. More than 2 centuries before that night in Berlin, in the winter, at the end of 1612 and the beginning of 1613, Galileo Galilei, the first human being ever to point a telescope at the night sky in earnest, was watching Jupiter and its moons. And in his notebooks from those nights, among the careful dots and sketches, there is a faint star drawn near Jupiter that we now know, from working the sky backward like a film run in reverse, was not a star at all. It was Neptune. Galileo saw Neptune. He recorded it twice. On one night he even seems to have noted that the little star appeared to have shifted slightly with respect to another. And then the weather turned, or Jupiter moved on, and the moment passed. He never knew. The first telescope ever aimed at the deep sky landed by pure chance on the last planet 234 years early, and nobody found out until both the man and his century were long gone. The universe does not hide things from us maliciously. It simply waits, patient beyond all human patience, for us to be ready to see what has been in front of us all along. And one more name belongs in this chapter, spoken a little more softly. Across the Channel in England, a young mathematician named John Couch Adams had been working the same problem as Leverrier, independently, and by some accounts had reached a broadly similar answer earlier. Through a tangle of missed meetings, unanswered letters, and observatory politics, the English search was slow and halting, and the prize went to Paris and Berlin. For years afterward, the two nations quarreled over credit, sometimes bitterly, while the planet itself, serene and indifferent, went on tracing the orbit it had been tracing since before either nation existed. In the end, history has mostly settled into generosity, remembering both men as the twin fathers of the prediction. Neptune, for its part, was named the way the other planets were named, for the old gods, and the name fit almost too well. The god of the deep ocean, remote and powerful and given to storms, for a planet that would turn out a century and a half later to be exactly that. So what exactly had they found that September night in Berlin? Let us build the world properly, piece by piece, because Neptune rewards a slow look. Start with its year. Neptune is so far from the Sun that one lap around its orbit takes almost 165 Earth years. Sit with that number the way we sat with the sunlight. A single Neptune year is longer than any human life that has ever been lived. If you were born on Neptune, you would not live to see your first birthday, not because the world is deadly, though it is, but because the calendar itself outlasts us. Since the night Galley and D'Arrest found it, Neptune has completed exactly one orbit of the Sun. One. The anniversary came in the summer of 2011 when the planet finally returned to the patch of sky where it had been discovered, one whole Neptune year after 1846. Everything that has happened since the discovery, the electric light, the telephone, 2 world wars, the atom split, the moon landings, the internet, every single human being alive today being born, all of it fits inside 1 year on Neptune. When people say the outer solar system runs on a different clock, this is what they mean. Neptune has been around the Sun perhaps 30 million times in its existence, and yet in the span of human knowledge, it is barely 1 lap old. Now the body of the planet itself. Neptune is the 4th largest planet by width, nearly 4 times as wide as Earth, a ball so large you could line up almost 4 Earths across its face. By weight, it is the 3rd heaviest, outmassing Uranus despite being slightly smaller, about 17 times the mass of our entire world. And yet, for all that bulk, Neptune is not solid. There is no surface anywhere on it that you could stand on, no ground, no sea, no ice sheet. It is a planet of atmosphere and fluid all the way down, thickening gradually from thin cold gas at the top to a dense, hot churn below. And if you tried to land on Neptune, you would simply fall and keep falling into pressures and temperatures that would destroy any machine we know how to build. Astronomers file it in a category it shares only with Uranus, not a rocky world like Earth and Mars, not a gas giant like Jupiter and Saturn, which are overwhelmingly hydrogen, crushed samples of the Sun that never caught fire. Neptune and Uranus are something in between, and the name scientists gave that category tells you what they think it is made of. They call them the ice giants. Deep beneath the hydrogen skin of Neptune, most of the planet's weight is water, ammonia, and methane, the same humble molecules you find in a kitchen and a cleaning cupboard, but gathered 17 Earths deep and compressed into states of matter that do not exist anywhere on our world. We will go down into that strange interior later tonight, all the way down, because the answer to the furnace, if there is an answer, is buried there. From the outside, though, what you notice first is the color. Neptune is blue, not the pale, milky blue-green of Uranus, but something deeper, the blue of open ocean in the photographs everyone has seen, and the chemistry of that color is simple and lovely. High in Neptune's atmosphere floats a small amount of methane, and methane has the property of swallowing red light. Sunlight arrives carrying every color at once, the reds go in and do not come back out, and what the planet reflects back at us is the light that survived, the blues. The planet is blue for the same reason a stained glass window is colored by subtraction, by what the material keeps. Though here modern astronomy asks us to hold the picture a little loosely, because in recent years researchers went back to the original spacecraft images and found that the deep marine blue we all grew up with had been enhanced, sharpened, and deepened in processing to bring out the details of the clouds. The truest Neptune, seen with honest eyes, is paler than its portrait, closer to its twin's soft greenish blue than the posters suggest. I find something almost endearing in that. Even the planet's famous face is partly a story we told, and the real world underneath is subtler, quieter, harder to pin down. That will become a theme tonight. Neptune spins fast for its size, turning once in about 16 hours, so its days are 2/3 the length of ours. Its axis is tipped over at an angle not far from Earth's, which means Neptune has seasons like ours, spring, summer, autumn, winter, in their proper order. But remember the length of the year. Each season on Neptune lasts around 40 years. A Neptune summer is a human career. A child born at the start of the planet's southern spring would be elderly before the first day of that hemisphere's summer arrived. Whole generations of astronomers have studied Neptune and never seen it change season more than once. And out there, of course, the seasons are not warmth and cold as we know them, only shades of cold, a shifting of which pole leans its long twilight toward the sun for 4 decades at a time. And what would that sun look like from the cloud tops? This is worth a moment because it is easy to imagine the outer solar system as a place where the sun has shrunk to just another star, and that is not quite right. From Neptune, the sun would be a point, yes, too small to show a disk, a fierce pinprick of white in a dark, blue-black sky. But it would be a devastating pinprick, still hundreds of times brighter than the full moon is on Earth, far too brilliant to look at directly. Noon on Neptune is not blackness. It is that deep, endless dusk we spoke of, bright enough to read by, dim enough that the stars might glimmer at the edges of the sky while the sun is up. Sunrise on a world where the sun is a rivet of light, a day where your shadow is sharp but faint. 4 hours behind that light, always, the rest of the solar system going about its business, unseen and unheard. When engineers talk about how hard it is to operate a spacecraft at Neptune, this is half of what they mean. So little light to power solar panels that they are useless there, and every radio message crawling 4 hours out and 4 hours back, so that a simple question and its answer takes a full working day. Which brings us, inevitably, to the only machine that has ever been there, and to 4 hours in the summer of 1989 that provided almost everything we know about this world up close. The spacecraft was Voyager 2, and even in a night dedicated to Neptune, we should give its journey its due, because there may never be another story quite like it. Voyager 2 left Earth in August of 1977, a machine roughly the weight of a small car carrying instruments designed in the era of slide rules and 8-track tapes. It was built for a rare opportunity, Once every 176 years or so, the outer planets arrange themselves in a long curve, such that a single spacecraft flung from Earth at the right moment can visit them one after another, borrowing speed from each in turn, a route the newspapers of the day called the Grand Tour. Voyager 2 flew it, Jupiter in 1979, Saturn in 1981, Uranus in 1986, and then 12 years and more than 4 billion miles of flying after it left Florida, its final port of call. On the 25th of August, 1989, Voyager 2 swept just 3,100 miles above Neptune's northern cloud tops. After all those years and all those worlds, that pass over Neptune's pole was the closest approach the spacecraft ever made to anything on its entire tour. The last visit was the most intimate. Engineers threaded it that low for a reason, using Neptune's gravity to bend the trajectory down toward one final target, the great moon Triton, whose story is waiting for us later tonight. There was nothing left to save fuel for. This was the end of the line, and they spent the mission's last inheritance on getting close. Think about the machine in that moment. Its radio transmitter broadcast with about 20 watts of power, the strength of a refrigerator bulb. Every picture it took had to cross the 4 billion miles home as a whisper of radio, arriving so faint that dishes on 3 continents were ganged together to hear it, and each signal took 4 hours and 6 minutes to make the trip. The controllers on Earth were not flying the spacecraft in any meaningful sense. Everything at Neptune happened on a script written weeks in advance and executed by a computer with less memory than a musical greeting card, 4 hours before anyone on Earth could know whether it had worked. And the risks that night were not abstract. To get its gravity assist down to Triton, Voyager 2 had to fly closer to Neptune than it had flown to anything in 12 years, skimming in over the North Pole, and the navigators had spent years worrying about what might be in the way. Nobody knew exactly where all the ring material was. Nobody knew how far the fringes of the atmosphere reached, or whether unseen moonlets or dust lurked along the approach path, and at closing speeds of tens of thousands of miles per hour, a fleck of ice the size of a grain of rice could have ended the mission in a heartbeat, 4 hours before anyone on Earth would even hear the silence. The team had already learned respect for such things at Saturn, where the spacecraft scan platform had jammed during the crossing years before. So the final approach was flown with a kind of held breath, spread across 3 continents. There was nothing anyone could do but wait for light that had already left. In the event, Neptune let the visitor through clean. The spacecraft threaded the gap, took its pictures, bent its path down past the pole, and came out the far side with every instrument singing, and the navigation, after 4 billion miles and 12 years of flying, arrived on target to within a handful of miles, and within moments of the planned time. People sometimes ask what humanity's most precise long-distance achievement is. There are grander-sounding candidates, but a fair case can be made for this one. A 70s-era robot aimed years in advance, arriving at the last planet at the far end of the solar system, on schedule almost to the second, on course to the width of a small town. And it worked. It worked almost perfectly. Through the late hours of that August night in Mission Control in California, the pictures came up on the screens line by line while the scientists who had waited 12 years crowded in with coffee, going cold in their hands. And a world that had been a fuzzy dot in every telescope on Earth resolved, at last, into a place. And what a place. The mission's planners had braced for disappointment. 3 years earlier, Uranus had greeted Voyager 2 with an almost featureless face, a smooth cue ball of haze, and Neptune was farther, colder, dimmer, with even less sunlight to power any weather. The reasonable expectation was blandness. What the cameras found instead was a planet in open revolt against that expectation. There, in the southern hemisphere, rode a storm the size of the entire Earth, a dark oval of deep blue-black cloud that the team named the Great Dark Spot, spinning and rolling like something alive, with bright white clouds of frozen methane smeared above it like cream stirred across ink. Nearby, a smaller bright cloud was whipping around the planet so quickly, coming around roughly every 16 hours, that the imaging team nicknamed it Scooter. There were shadows of clouds cast down onto cloud decks miles below, the first cloud shadows ever photographed on another world of this kind, which told the scientists at a glance that the atmosphere was tall and layered and dynamic. And when they clocked those racing clouds against the planet's rotation, out came the number that gives tonight its title: winds tearing westward past 1,200 miles per hour, the fastest sustained winds ever measured on any planet in the solar system, on the world that receives the least sunlight of any planet in the solar system. The stillest place turned out to be the wildest. One scientist at the time compared the surprise to arriving at the quietest house on the street and finding a hurricane living in it. The haul from those few days rewrote the textbooks front to back. Voyager 2 found 6 new moons in the space of a week, small dark bodies circling close in, more than doubling the known family at a stroke. It confirmed that Neptune has rings, thin, dark, dusty hoops that telescopes on Earth had only half glimpsed, including one ring gathered mysteriously into bright clumps like beads on a wire, which should not have been able to last, and yet there they were. It measured the planet's magnetic field and found it bizarre, tilted at nearly 50 degrees from the spin axis and offset from the planet's center, as though someone had shoved the bar magnet deep into one side of the world at a drunken angle. That finding deserves a moment of its own, because it quietly points at everything we will explore in the deep interior later tonight. Earth's magnetic field is generated near our planet's center, in the churning liquid iron of the core, and it emerges aligned, more or less, with our spin, which is why a compass works and why the auroras ring the poles. Neptune's field is nothing like that. It is lopsided, off-center by a huge fraction of the planet's radius, tipped drunkenly away from the rotation axis, and it had no right to be either of those things unless it is being generated somewhere unexpected, not in the core at all, but in a comparatively shallow shell partway down, where scientists now believe electrically charged water and ammonia, squeezed until they conduct like metals, swirl and regenerate the field. In other words, the compass needle of Neptune told us, before we could look any other way, that the inside of an ice giant is not built like the inside of anything else we knew. Uranus, it turns out, has a field just as strange, tilted and offset in its own drunken direction. So this is evidently what ice giants do. Every time Neptune rotates, its lopsided field tumbles through space in a pattern one team memorably compared to a badly thrown football, wobbling end over end, dragging its magnetic bubble through the solar wind in a rhythm no other planet keeps. It took Neptune's temperature and confirmed the furnace, the heat pouring out at more than twice the solar allowance. And then, with its cameras turning back for one last look at a thinning blue crescent, Voyager 2 fell away past Triton and out of the planetary solar system forever, its grand tour complete, bound for interstellar space with no brakes and no way home. Here is the fact I keep returning to, the one I most want you to carry out of tonight. That flyby lasted, in its intense close phase, a matter of hours, a single working day at the office, more or less. And in the decades since, no spacecraft has returned to Neptune. None is on its way tonight. None has even been formally approved to go. Nearly everything humanity knows about the eighth planet up close, the storms, the winds, the strange magnetic field, the close portrait of its great moon, every sharp image in every textbook, traces back to that one brief pass in the last summer of the 1980s, executed by a machine older than most of the people now studying its data. Astronomers have worked wonders from Earth in the years since, as we will hear, and the great space telescopes check in on Neptune faithfully. But there is only so much you can learn about a house from across the street. We knocked on Neptune's door exactly once. The door opened, we saw wonders for an afternoon, and we have been standing at the end of the driveway ever since, remembering. An entire world, 17 times the mass of ours, running the wildest weather in the sun's family, and our whole close acquaintance with it fits inside a summer afternoon that happened before most of the people alive today were born. Now, let us take the winds seriously, because it is easy to say 1,200 miles per hour and move on, and I do not want to move on. I want you to feel how wrong that number is, and then I want to walk through what it would take to explain it, because the explanations are almost as strange as the mystery. Start at home. Wind on Earth is sunlight in motion. Every breeze you have ever felt began as unevenness, one patch of the world heated more than another, air expanding and rising over the warm patch, cooler air sliding in underneath to take its place. The whole roaring machinery of our weather, the trade winds, the jet streams, the monsoons, the hurricanes, is powered by the simple fact that the sun heats the equator harder than the poles and the surface harder than the heights. Our planet drinks in an enormous river of solar energy every second, And even so, the fastest sustained winds our atmosphere ever manages in the hearts of the very worst hurricanes are a bit over 200 miles per hour. The most violent tornadoes may briefly touch 300 in a funnel a few hundred yards wide. That is Earth's ceiling, running on a torrent of sunshine. Now walk outward and watch what happens to the winds as the sunlight fades. At Jupiter, 5 times farther from the sun than Earth, the sunlight has thinned to a 25th of ours, and yet the winds are faster, not slower. Jupiter's great banded jets run at 300 or 400 miles per hour, and its storms are large enough to swallow our whole world. Continue to Saturn, nearly twice as far again, where the light is 100th of what falls on Earth, and the winds rise again, with jets near the equator that have been clocked at over 1,000 miles per hour, and then go all the way out to the edge, to Neptune, where the sunlight is down to 1 part in 900, the barest trickle of energy, the dimmest weather budget of any planet, and there you find the fastest winds of all, sustained rivers of air past 1,200 miles per hour. And it is worth pausing on how anyone can even know such a thing, because there are no weather stations on Neptune, no anemometers spinning on poles. The method is patient and almost absurdly simple. You find a cloud, a bright smear of methane ice distinctive enough to recognize, and you photograph it, and then you photograph it again hours later, and you measure how far it traveled against the body of the planet, distance over time. The same arithmetic a child does with a paper boat on a stream. The Voyager scientists did it frame by frame through the approach, watching their chosen clouds lap the planet, and astronomers with the great telescopes have done it ever since, and the answers keep coming back in the same impossible range. There is an added wrinkle that makes the numbers even stranger. To measure a wind, you need to know what still would mean, and on a world with no surface, still can only mean the rotation of the deep interior, which we read from the radio pulses of the magnetic field. Measured against that inner clock, Neptune's equatorial winds do not blow eastward with the spin, the way most of Earth's great winds do. They blow backward, westward, against the planet's rotation, a globe-girdling river of air running retrograde at those tremendous speeds. The planet turns one way, and its atmosphere, at the equator, streams the other, like a carousel spinning under a canopy that swirls in reverse. Do you see the shape of it? Across the solar system, as a broad rule, less sunlight has somehow meant more wind. The trend runs exactly backward. It is as though you visited a series of houses, each with a smaller fireplace than the last, and found each one warmer inside. By the time you reach Neptune, the fireplace is almost cold, and the house is roaring. Any honest engineer, handed the solar numbers alone, would have designed Neptune's atmosphere to be a sluggish, foggy pond. Nature built a racetrack. How is that possible? The leading ideas come in 2 parts, and both of them will sound almost paradoxical at first hearing. The first part says this: sunlight does not only power winds, sunlight also kills winds. All that solar energy pouring into Earth's atmosphere does not just push air around, it stirs it, breaks it up, fills it with rising columns and sinking sheets, and swirling eddies of every size, and all of that turbulence acts like friction. Every storm is a break on the larger flow. Think of our jet streams constantly buffeted, bent, and robbed of speed by the churning weather beneath them. Now take the sunlight away. Out at Neptune, the atmosphere receives so little stirring energy that, by these models, it may be far smoother, far less turbulent than ours. Fewer eddies, less churn, less friction. And in an atmosphere with almost nothing to slow it down, even a weak, patient push can build tremendous speed over time, the way a hand on a heavy flywheel, pushed gently but steadily for years, can spin it up to a blur. Neptune's winds may be fast, not in spite of the darkness, but partly because of it. The quiet out there is so deep that the air can keep every mile per hour it ever earns. On Neptune, nothing tells the wind to stop. Measurements support a version of this picture in one striking way. Careful analysis of the planet's gravity field from the flyby data suggests that the furious winds are surprisingly shallow, confined to an outer layer of the atmosphere, perhaps 600 miles deep, a skin of racing weather on a body nearly 31,000 miles across. Beneath that skin, the deep interior seems to rotate more or less as one body, sluggish and unified. If that is right, then all the violence we see is a thin, glittering frenzy on the surface of something slow and vast, like whitecaps on a deep, dark swell. I find that image stays with me. The fastest winds in the solar system may be only a few hundred miles thick, a bright ribbon of fury wrapped around a sleeping giant. But shallow or not, the winds still need an engine, and that brings us to the second part of the answer, the part that Voyager confirmed and nobody has fully explained since: the furnace. Neptune radiating 2.6 times the energy it receives is not a small bookkeeping error. It means the planet has its own internal supply of heat rising up from below, and in the darkness of the outer solar system, that inner heat is not a minor contributor to the weather. It is the main event. At Neptune's distance, the trickle of warmth seeping up from the planet's depths is comparable to, and in the deep atmosphere greater than, everything the sun provides. The temperature difference between the day side and the night side of Neptune is almost nothing, because the sun matters that little there. The planet's weather is powered from underneath, heat rising from the interior, the way heat rises from the bottom of a heated pot, driving convection, feeding the jets, keeping the storms alive through decades of darkness. When you look at a picture of Neptune's clouds, you are not really looking at solar weather at all. You are looking at the planet's own body heat, made visible. The storms of Neptune are the surface expression of something happening thousands of miles down in a place no camera will ever see. The great dark spot itself deserves one more look before we go inside, because the closer Voyager got, the stranger the great storm became. It was not a fixed feature like a whirlpool anchored to a rock. Through the months of approach photography, the spot changed shape continuously, stretching and relaxing, its edges rippling, the whole oval flexing like something breathing. It rolled counterclockwise, an anticyclone like Jupiter's great red spot. But where the red spot is a stubborn, settled institution, the dark spot behaved like a young animal, restless, wobbling in its lane, drifting against the flow of the surrounding jets. Above it floated those brilliant white companion clouds, methane ice crystallizing where the storm shoved deep air upward into the cold, remaking themselves hour by hour, never the same twice, some of the fastest changing clouds ever photographed on any planet. And the darkness of the spot is its own small riddle. It is likely a window rather than a stain, a place where the vortex has cleared the upper haze and we are seeing down into the deeper, darker blue of the atmosphere below, a hole in the clouds the size of a world held open by rotation. All of that, remember, was observed across a few weeks of approach. That is the maddening arithmetic of studying Neptune. Our single close look at its greatest storm caught a few flexes, a few turns, a few weeks in the life of something that, for all we knew then, might live for centuries. It did not live for centuries, but we are getting ahead of the story. So the real question is not why is Neptune windy? The real question is why is Neptune still warm 4.5 billion years after it formed? And to reach for that answer, we have to do something no spacecraft can do. We have to go down. So let this be tonight's first long descent. Breathe out, let yourself sink, and come with me. Down through the cloud decks of the last planet, because the journey from the top of Neptune's atmosphere to its heart is one of the strangest trips the solar system offers. We begin at the cloud tops in that deep twilight we described, the sun, a brilliant rivet low in a blue-black sky. It is bitterly cold here, near -200 degrees Celsius, cold enough that the wisps of cloud around us are not water, but crystals of frozen methane, thin white streaks drawn out by the wind into lines hundreds of miles long. The air is mostly hydrogen, with helium mixed through it, thin and utterly transparent. And it is moving. Even here at the top, we are being carried sideways at hundreds of miles per hour, though strangely, with nothing around us but smooth air, we would barely feel it. Fall now, let go, and sink. The light dims by the mile. The pale blue of the sky above deepens through violet toward black, and the pressure begins to climb, gently at first, then insistently. Within the first few dozen miles, the methane clouds are above us, and the temperature, oddly, has begun to rise, warmed not by the sun, which is losing its grip on us already, but by the pressure of the deepening air itself and by the steady heat welling up from below. We pass through decks of stranger clouds, sheets that chemists believe are crystals of hydrogen sulfide and ammonia. The whole sky above us, now a dim grey-green ceiling, the last blue light scattering away. 100 miles down, 200, and the darkness closes completely. From here on, Neptune makes its own conditions. No sunlight has ever reached this deep. No sunlight ever will. Keep sinking, and the world thickens around you. The hydrogen air compresses toward the density of water, and somewhere in the deep gloom, perhaps a few thousand miles down, there are thought to be clouds of actual water, a level where the temperature has climbed back past the boiling point, even as the pressure has risen to thousands of times what we live under. The atmosphere is no longer really a gas here, and not yet quite a liquid, just an ever-thickening hot fluid, black as the inside of a stone, crushing inward, growing hotter with every mile. And below that begins the true body of the planet, the region that gives the ice giants their name, a vast, deep ocean, thousands of miles thick, of water, ammonia, and methane compressed into a state scientists call a superheated, superpressurized fluid. Do not picture an ocean you could swim in. The temperatures down here run to thousands of degrees, far hotter than any oven, and the pressures run to millions of Earth atmospheres, and under those conditions, water stops behaving like anything we know. Experiments and models suggest that deep inside Neptune, water may take the form of something called superionic ice, a black, hot, solid lattice of oxygen through which hydrogen pours like a liquid, ice that is simultaneously solid and flowing, ice at thousands of degrees, ice as hard as steel and as strange as anything physics has ever cooked up. The floor of that impossible ocean, at last, is a core of rock and iron, perhaps the size of the Earth, and the temperature there is thought to rival the surface of the sun. Hold that thought squarely. At the center of the coldest, dimmest, most distant planet, there burns a knot of matter as hot as the star it circles. Neptune carries a piece of sunfire in its heart, sealed under an ocean of black ice, and has carried it slowly leaking for 4.5 billion years. Some of that heat is simply leftover birth. When Neptune assembled itself out of the early solar system's debris, every impact, every infalling comet and colliding embryo converted its motion into warmth, and a body 17 times the mass of Earth, wrapped in insulating layers thousands of miles thick, loses that primordial warmth very, very slowly. Part of the furnace is just the long cooling of creation, the same reason a loaf of bread is still warm at the center an hour out of the oven. But the accounting never quite closes with leftovers alone, and so scientists have gone looking for stranger fuels, and here the story takes a turn so marvelous that I would not blame you for thinking I had drifted into a bedtime fairy tale. I have not. This is real, published, laboratory-tested science. Deep inside Neptune, it may be raining diamonds. Follow the logic, because every step is solid. Neptune's interior is rich in methane, and a methane molecule is one atom of carbon holding 4 atoms of hydrogen. At the temperatures and pressures a few thousand miles down, thousands of degrees, millions of atmospheres, Methane cannot survive. The molecule is torn apart, and the freed carbon atoms, squeezed beyond anything on Earth, do what carbon does under ultimate pressure. They bond into the hardest, densest arrangement carbon knows. They crystallize into diamond, and diamond is heavy, far denser than the hot fluid around it, so the crystals do not float where they form. They fall. They sink through the deep ocean of Neptune like stones dropped in honey, gathering, growing. As they descend through carbon-rich layers, a slow-motion downpour of gemstones drifting through thousands of miles of black heat toward the core, perhaps over thousands of years for a single stone's journey. Some researchers suspect the diamonds pile into layers around the core, an actual stratum of diamond, or dissolve back into the deeper heat, or even in the most vivid models form drifts and bergs in liquid carbon seas. And for a long time this was pure theory, beautiful and untestable. Then, in 2017, a team at a laboratory in California decided to try it. They took a piece of plastic, polystyrene, chosen because its mix of carbon and hydrogen resembles methane, and they struck it with one of the most powerful lasers on Earth, driving shockwaves through it that, for the briefest instant, recreated the pressure and temperature conditions of Neptune's interior, over 1 million atmospheres and thousands of degrees at once. And to catch what happened in that instant, they fired an X-ray laser through the sample in flashes lasting 50 millionths of a billionth of a second each, fast enough to photograph chemistry itself in the act. The X-rays came back carrying an unmistakable signature: diamond. Nearly every carbon atom in the plastic had slammed together with its neighbors into tiny crystals, nano-diamonds, diamond dust conjured out of squeezed plastic in a fraction of a heartbeat. The experiment has been repeated and refined since, with the diamonds forming even more readily than the first tests suggested. The fairy tale, as far as we can test it from Earth, checks out. Under Neptune's conditions, diamonds happen. Diamonds are, in a sense, the local weather. And here is the beautiful closing of the loop, the reason the diamond rain belongs in tonight's mystery, rather than just in tonight's wonders. Falling matter releases energy. Every diamond that sinks through Neptune's interior gives up its energy of position as friction and heat in the fluid it falls through, exactly the way a meteor heats the air it plunges into. It is not a large effect from any single stone. But a planetary interior raining gemstones continuously for billions of years is not a single stone. And models suggest that this slow diamond drizzle, this settling of heavy matter toward the center, could be a real and possibly substantial contributor to Neptune's mysterious extra heat. Sit with that image for a moment, because I think it is one of the finest the solar system has to offer. The fastest winds in the sun's family, the storms that dwarf the Earth, the great dark ovals rolling through the blue, all of it powered, in some part, by diamonds falling in the dark. A world where the rain is made of jewels, and the jewels falling keep the storms alive. If you drift off around now, let it be with that. Somewhere out there tonight, 2.8 billion miles above your bed, it is raining diamonds inside a blue planet, and the storm over the cloud tops is the sound that rain makes. But now we have to face the twin, because everything we have just built, the furnace, the diamond rain, the heat leaking up from creation, runs straight into the quiet problem waiting one orbit inward, Uranus. If Neptune's inner heat is just the natural leftover warmth of building an ice giant, then Uranus should have it too. The two planets are as close to siblings as the solar system ever produced. Uranus is a shade wider, Neptune a fair bit heavier, but they are the same kind of object to a degree that no other pair of planets can match, formed in the same era, from the same neighborhood of the Sun's birth cloud, out of the same inventory of rock and ice and gas. Two puddings from the same recipe, baked in the same oven. Every reason Neptune should be warm applies to Uranus with almost equal force, and Uranus is not warm. The measurements, first from the flyby and refined since, put the two planets in different worlds of bookkeeping. Neptune pours out roughly 2.5 times its solar income. Uranus emits barely more than it absorbs, a few percent over break-even by most estimates, so little that some analyses over the years have struggled to prove it emits any excess at all. However you cut the numbers, the gulf is enormous. One twin has a furnace, the other has, at most, an ember. Nobody knows why. I want to be plain about that, because it is rare and precious in a field this mature. This is not a case where scientists have the answer and are dotting the details. The thermal difference between Uranus and Neptune is a genuine open problem, decades old, still argued at conferences, and every proposed solution ends up leaning on the strangest single fact we know about Uranus. Uranus is lying on its side. Every other planet in the solar system spins more or less upright as it circles the Sun, axes tilted here and there by modest angles, Earth at 23 degrees, Neptune at 28. Uranus is tipped over at 98 degrees, passed sideways its poles where its equator should be, rolling around its orbit like a barrel on a track, while its family of moons and rings circles its middle like a Ferris wheel. Something did that to Uranus. The reigning suspicion, though it remains a suspicion, is a catastrophe in the planet's youth, a collision with a wandering body perhaps the size of the Earth, or larger, a blow titanic enough to knock a giant planet off its feet permanently. And ever since the two heat measurements came in, scientists have wondered whether the same ancient blow explains both oddities. Perhaps the impact that tipped Uranus also emptied it, splashing out or stirring up its deep interior so violently that its primordial heat escaped early, venting in a geological instant the savings that Neptune has been spending gradually for billions of years. In that story, Uranus is cold because it was robbed in its childhood, and Neptune is warm because it was left alone. But there is a rival story, and I confess it is the one that keeps me up at night in the best way. In the rival story, Uranus has not lost its heat at all. The heat is still in there, all of it, locked in. In this picture, The deep interior of Uranus is layered like a parfait, stable strata of different compositions that refuse to mix, and those layers act as insulation, shutting down the great convective conveyor belts that would otherwise carry inner heat to the surface. The furnace burns on beneath a closed door. Meanwhile, Neptune's interior, for some reason of history or chemistry, convects freely, its door wide open, its heat streaming up to power the storms. If that is the truth, then the difference between the dead twin and the violent twin is not a difference of wealth, but a difference of plumbing. And somewhere under Uranus's bland face there is a hidden ocean of trapped fire waiting for a door that may never open. Two stories then, Uranus the robbed or Uranus the sealed, an ancient catastrophe or a quiet quirk of layering. The honest answer is that we do not know, and we may not know until spacecraft finally orbit both worlds with modern instruments, and when the answer comes it will tell us not just about two distant planets, but about what happens inside every ice giant. And ice giants, as it turns out, appear to be one of the most common kinds of planet in the entire galaxy. Astronomers surveying other stars keep finding worlds in the Neptune size class over and over, far more often than worlds like Jupiter. The galaxy, it seems, loves making Neptunes, which means the unsolved argument between these two particular twins is really an argument about one of the most common kinds of place there is, the most ordinary planet in the galaxy, and we cannot yet say why one copy of it burns and the other does not. The universe keeps its best homework problems close to home, and Neptune has one more marvel that Uranus cannot match, one more piece of luck or larceny that sets the twins apart, and it is time we met it, because it may be the single strangest object in the outer solar system. Neptune has a moon called Triton, and almost nothing about Triton is right. It was found with almost indecent speed. Word of the new planet's discovery crossed Europe in the first days of October 1846. And in England, a wealthy amateur astronomer named William Lassell turned his homemade telescope toward it. Lassell was a brewer by trade. He had made a fortune making beer in Liverpool, and he had spent that fortune grinding and polishing some of the finest telescope mirrors in the world, a hobbyist operating at the level of national observatories. 17 days after Neptune was discovered, before the planet had even properly settled into the textbooks, Lassell spotted a point of light keeping station beside it. A moon. The planet found by mathematics had a companion found by a beer fortune 2.5 weeks later. For more than a century, Triton was little more than that point of light, but even the point was enough to reveal something deeply wrong. Astronomers tracking it found that Triton orbits Neptune backward. Every large moon in the solar system, ours included, circles its planet in the same direction the planet spins, because moons and planets condense together from the same swirling disk, the way everything in a whirlpool turns the same way. Dozens of large moons around Jupiter, Saturn, Uranus. Every single one orbits forward. Triton, alone among all the large moons in the solar system, orbits in reverse against Neptune's spin, the one commuter driving the wrong way down the freeway. And in celestial mechanics, that is not a quirk. That is a confession. A large moon in a backward orbit cannot have been born there. It had to have been captured. Triton is not Neptune's child. Triton is Neptune's prisoner. Where did the prisoner come from? Size gives the first clue. Triton is about 1,700 miles across, a hair bigger than Pluto, and when spacecraft finally saw both worlds up close, the family resemblance was unmistakable. The same nitrogen ice surfaces, the same pinkish frosts, the same class of body in every measurable way. Triton and Pluto are siblings. They are both natives of the Kuiper Belt, the vast ring of icy worlds beyond Neptune that we will visit properly later tonight. And at some point in the deep past, Triton's path brought it too close to the last giant planet. How Neptune caught it is its own lovely puzzle, because planets cannot simply grab things. An object falling past a planet speeds up on the way in and spends every bit of that speed on the way out, escaping as surely as it arrived, unless something takes energy away from it at exactly the wrong moment. The leading idea, published and much studied, is that Triton did not arrive alone. It arrived as half of a pair, two icy worlds orbiting each other as they wandered, a binary which the Kuiper Belt makes in abundance, Pluto and its huge moon Charon being the famous surviving example. When the pair swung past Neptune, the encounter split them. One partner was flung away into the dark at tremendous speed, carrying off the pair's excess energy, and the other, Triton, was left behind, too slow to escape, falling into Neptune's keeping forever. If that is what happened, then somewhere out there tonight, wandering the galaxy or lost in the far reaches of the sun's domain, there is a world that was once Triton's companion, exiled so that Triton could be caught. Astronomy is full of quiet tragedies like that, written in orbits with no witnesses. The capture was only the beginning of the violence. A freshly caught Triton would have started on a wild, elongated orbit, and Neptune's tides went to work on it, kneading the moon on every pass the way you knead dough, and that kneading had two effects. It circularized the orbit over millions of years into the nearly perfect ring Triton rides today, and it melted the moon. The tidal working of that era likely turned Triton's interior molten, resurfacing it wholesale, boiling off ancient terrain, leaving the strangely young, smooth, creased face that would one day astonish the cameras. And there was collateral damage. Neptune almost certainly had its own family of original moons before Triton arrived, a normal, orderly system like the ones Jupiter and Saturn and Uranus keep. A massive body barreling in on a backward orbit would have shattered that family, scattering some moons into the planet, hurling others into the dark, grinding still others against each other into rubble. The odd assortment of small moons Neptune keeps today, and that strange clumped ring system, are thought to be the wreckage and the aftermath, a second generation cobbled together from the debris of the first. When Triton came, Neptune's household was destroyed and rebuilt around the newcomer. The prisoner did not just join the family, the prisoner replaced it. Today, Triton so dominates the system that it accounts for the overwhelming share of all the mass orbiting Neptune. One moon holding almost everything on a backward orbit, circling the scene of the crime. Then, in the last hours of its mission, Voyager 2 arrived, and the prisoner turned out to be alive. The flyby had been threaded, remember, to end at Triton, and as the images came home line by patient line, the scientists found themselves looking at one of the most unexpected worlds of the entire space age. Triton's surface is nitrogen ice and frozen methane, sculpted into a terrain seen nowhere else. A dimpled, ridged landscape the team compared to the skin of a cantaloupe, cut by long, dark seams like the seams of a baseball. Its temperature, measured at minus 235 degrees Celsius, the coldest surface temperature ever measured on any large world in the solar system. Cold enough that the moon's thin nitrogen atmosphere freezes out onto the ground in winter as bright polar frost. Nothing about a world like that should move, and things were moving. Across the frostlands of the South Pole, the cameras caught dark streaks smeared across the ice, dozens of them, all combed in the same direction by thin winds, and then, incredibly, they caught the streaks being made. Geysers, columns of dark material and nitrogen gas jetting miles up off the surface, rising like sweet soak from chimneys on the coldest world ever measured, drifting downwind and settling in long shadows on the frost. On a moon where the very air lies frozen on the ground, something is warm enough, just barely, to erupt. The best guess is a kind of solid greenhouse, sunlight, faint as it is out there, sinking into translucent nitrogen ice and warming dark material trapped beneath it, until pockets of nitrogen boil into gas and blast free. Some researchers suspect something deeper, true geological plumbing, perhaps connected to the moon's greatest secret, because the tidal melting of Triton's youth and the radioactive warmth of its rocky interior may have left it with what so many icy worlds now seem to hide: an ocean, a layer of liquid water, dark and sealed, buried beneath the ice shell, kept unfrozen through the ages. If it exists, it is one of the most remote possible cradles for life we know of, a sunless sea inside a stolen moon, at the edge of everything, and no one will see it in our lifetimes. The evidence is circumstantial. The possibility, though, is now taken seriously enough that mission planners speak of Triton in the same breath as the famous ocean moons of Jupiter and Saturn. The coldest world we have ever measured may be warm somewhere deep down in the one place we cannot look, and Triton is falling. This is the last movement of its story, and it is already underway tonight. Because Triton orbits backward, the tides between it and Neptune work in reverse. Our own moon, orbiting forward, is slowly being pushed away from Earth, drifting outward about 1.5 inches per year, gaining altitude at the expense of Earth's spin. Triton, running against Neptune's rotation, gets the opposite bargain. The tides it raises drag against it, sapping its orbit, and so with every backward lap, Triton spirals imperceptibly inward, down toward the planet that captured it. The fall is patient beyond imagining, but it is a fall, and the ending is already computed. Billions of years from now, on the order of 3.6 billion by the standard estimate, Triton will descend to the invisible boundary called the Roche limit, the altitude below which a planet's gravity pulls harder on a moon's near side than the moon's own gravity can hold it together. At that line, Triton will not crash into Neptune. It will come apart, torn into rubble and ice and dust, ground down and smeared out along its orbit. The great backward moon will become a ring, and calculations suggest it could become a ring system to rival or exceed Saturn's, a colossal bright halo around the blue planet, gleaming in the twilight at the edge of the solar system. Perhaps some future watcher will see it and wonder what died there. The moon that was stolen will be unmade by the thief, and the evidence of the whole affair will hang around Neptune like a crown. But that is for a night billions of years from now. Tonight, Triton is whole and cold and quietly volcanic, gliding backward through Neptune's sky with its frost gleaming in a sunlight 900 times fainter than yours, still keeping the secret of where it came from and of whatever ocean sleeps inside it. Before we leave it, stand there for a moment. Let this be tonight's second long look, and let it be slower than the first. You are on the frost plains of Triton's southern hemisphere, and the ground beneath you is nitrogen ice, faintly pink where the frost has aged, glowing dimly in a light like the last 10 minutes of a winter dusk. The sun is up, if you can call it that, a hard, brilliant star too small to warm your face, hanging in a black sky. Your shadow stretches away from you, sharp-edged and faint at once. It is quiet in a way no place on earth is quiet, the thin whisper of an atmosphere, tens of thousands of times sparser than ours, carrying almost no sound at all. And then you lift your eyes, and there is Neptune, not a light in the sky, a presence. The planet hangs enormous above the horizon, many times wider than the full moon appears from Earth. A vast, dim blue ceiling to the world, half in shadow perhaps, its pale bands just visible, and if your timing is lucky, somewhere on that huge face, a dark storm the size of your whole home planet, rolling silently. It does not rise or set, not really, in the ordinary way of moons and suns, because Triton keeps one face toward its captor forever, the way our moon does toward us. Neptune simply stays, fixed in its station in the sky, the unmoving landlord of the horizon, while the far-off sun wheels slowly past. Behind you, somewhere out on the plains, a geyser is smoking, a thin, dark thread climbing miles into the twilight and bending over in the high wind like ink dropped into water. Under your boots, the ice creaks down toward a darkness that may hold an ocean no one will ever swim in. And beneath everything, too slow to feel, too certain to stop, the whole world you are standing on is falling, an inch at a time, across 3 billion years toward the blue giant that owns the sky. Of all the worlds we will never walk on, I think Triton may be the one I wonder about most. The rest of Neptune's household deserves its hour too, because the wreckage Triton left behind has arranged itself into some of the oddest furniture in the solar system. Start with the rings, because Neptune should not really have been expected to keep any, and what it keeps is stranger than mere rings. They are nothing like Saturn's broad, bright sheets of ice. Neptune's rings are thin, dark, and faint. Hoops of dust and debris so tenuous that from Earth, for years, astronomers could not even agree they existed. Through the 1980s, observers watching Neptune pass in front of the background stars kept getting contradictory answers. Sometimes the star blinked briefly before or after the planet crossed it, as though something thin had cut its light, and sometimes it did not blink at all. The same test, repeated, giving different answers, which is the sort of thing that drives scientists to distraction. The data suggested something impossible, rings that were only partly there, arcs, fragments of circles, and the physics of the time said that could not be. A partial ring should not survive. Any arc of debris orbiting a planet gets sheared by simple orbital mechanics, the inner edge moving faster than the outer, so that within a few years, any clump should smear itself evenly around the whole circumference. Arcs were forbidden. And when Voyager 2 arrived, there the arcs were forbidden and real, bright clumps strung along the outermost ring, like beads spaced on a thin wire, defying the shear that should have erased them. The French astronomers who had helped find them gave the brightest arcs names from their revolution: liberty, equality, fraternity, later joined by a fourth, called courage, and the leading explanation for their survival is a delicate gravitational trick. A small moon called Galatea, orbiting just inside the ring, herds the debris with its rhythmic tugs, corralling the particles into pockets the way a sheepdog holds a flock, resonance standing in for fences. Even so, the arrangement seems fragile, and here is the detail that makes Neptune's rings feel almost alive. They are changing. Observations from Earth in the decades since the flyby suggest the arcs are evolving, some fading and slumping toward dissolution. The one named Liberty reported at times to be dimming, as though it might disperse entirely within a human lifetime. We may be looking at something temporary, debris from some geologically recent smash-up among Neptune's small moons, still settling, still dissolving, a ring system caught in the act of dying. Around most planets, the architecture feels eternal. Around Neptune, even the rings are weather. The small moons themselves read like a casualty list from the Triton catastrophe, patched up and soldiering on. The largest of them, Proteus, is a dark, battered lump about 260 miles across, one of the largest, genuinely non-round bodies known, a world that is almost but not quite heavy enough for gravity to have crushed it into a sphere. It hugs Neptune so closely and reflects so little light that Earth-bound telescopes never saw it, a body wider than many famous moons, hiding in plain sight until 1989. Then there is Nereid, found back in 1949 by Gerard Kuiper himself, the astronomer whose name would later be attached to the great belt beyond Neptune. Nereid rides the wildest orbit of any large moon in the solar system, a huge wandering ellipse that swings it from under 1 million miles of Neptune out to almost 6 million and back on every lap, a path so lopsided that many suspect Nereid is another survivor of the Triton disruption, an original moon half thrown away, left dangling on the edge of escape for 4 billion years, the child that was flung toward the door and caught the frame. And at the small end of the family there is Hippocamp, a discovery of the modern era, first glimpsed in 2013 by astronomers stacking long sequences of space telescope images until a speck, barely 20 miles wide, swam up out of the noise. Hippocamp orbits startlingly close to the much larger Proteus, and its likeliest origin story is written in a giant crater that Proteus carries. Long ago, something enormous struck Proteus, blasting debris into orbit, and Hippocamp appears to be a chip off that impact, a splinter of a moon orbiting beside the wound it came from. Neptune's whole retinue is like this. Nothing out there is pristine. Everything is a survivor, a fragment, a rebuilt remnant of older violence, a family album where every photograph shows a scar. And this pattern, once you see it, keeps widening, because Neptune's influence does not stop at its rings and moons. Neptune is the shepherd of the entire edge of the solar system, and its flock is vaster than anyone suspected when the planet was found. Beyond Neptune's orbit begins the Kuiper Belt, the third zone of the solar system, a colossal ring of icy worlds and worldlets, billions of them, circling in the dark from Neptune's doorstep outward, of which Pluto is merely the most famous citizen. Through the middle of the 20th century, the belt was only a conjecture, and its confirmation in the 1990s redrew the map of everything past the 8th planet. But the belt is not a random scatter. It has structure, gaps, and clusters, and combed-out families, and nearly all of that structure has a single author: Neptune. The last giant's gravity, sweeping around the sun every 165 years, has spent 4.5 billion years organizing everything beyond it, clearing some orbits, protecting others, capturing whole populations into gravitational lockstep. Pluto is the showpiece. Pluto's orbit is so stretched that at times it actually comes closer to the Sun than Neptune does, their paths interleaved in a way that sounds like it must end in disaster. It never will, and the reason is a resonance. For every 3 orbits Neptune completes, Pluto completes exactly 2, a ratio Neptune's gravity itself enforces, and the geometry of that lock guarantees that whenever Pluto crosses the danger zone, Neptune is always somewhere else, far around the curve of its orbit. The 2 worlds repeat their whole dance every 500 years or so, and every repetition keeps them apart. Pluto cannot hit Neptune. It is not luck. It is choreography, choreographed by Neptune, and Pluto is not alone in the pattern. Hundreds of other bodies are caught in the same 3 for 2 lock, an entire tribe of small worlds that astronomers call, in Pluto's honor, the Plutinos, all of them stepping to Neptune's beat, all of them safe because the last giant conducts them. There are other tribes at other rhythms, 2 to 1, 5 to 2, an architecture of nested rhythms spreading across billions of miles, and at the center of the metronome, the planet nobody can see without a telescope. The deepest part of this story is that Neptune was not always where it is tonight. The evidence written into the Kuiper belt, those captured tribes, the combed structure, the sheer strangeness of how much stuff is locked to Neptune's rhythm, has convinced most planetary scientists of something remarkable. Neptune migrated. In the young solar system, the models say, Neptune formed noticeably closer to the Sun than we find it now. And then, over hundreds of millions of years, it moved. The engine was the debris itself. Every time Neptune slung a small icy body inward, the recoil nudged the planet a whisper outward, and quadrillions of such nudges walked the giant slowly out into the dark, ploughing through the primordial belt as it went, scattering some worlds into deep space, flinging others toward the inner planets, and gathering the lucky ones into those resonant tribes, herding them ahead of it like a slow tide pushing shells up a beach. Pluto itself was likely swept up this way, collected into its 3 for 2 lock and carried, orbit by orbit, into the arrangement it keeps today. Which means the structure of the entire outer solar system is, in a real sense, a footprint. The edge of the Sun's family is shaped the way it is because Neptune walked there, and everything beyond the 8th planet is either something Neptune herded, something Neptune exiled, or something Neptune left alone. And do not forget where we have already seen a Kuiper belt native tonight: Triton. The great backward moon is a captured belt object, which makes Neptune the only planet whose largest moon is a piece of the very frontier it governs. Neptune reached into the belt and took a citizen for a companion. The shepherd keeps one of the flock beside it on a leash of gravity, falling ever so slowly inward. Seen from far enough away, the whole outer solar system is really just Neptune's estate. The rings are its fences, half fallen. The moons are its rebuilt household. The belt is its garden, planted in rows it raked itself billions of years ago. And the gardener is invisible from the road. Neptune's reach does not even stop at the belt. And this next part I love, because it connects the farthest planet to lights people have actually seen with their own eyes. Beyond the main belt, scattered on wilder, longer orbits, there is a population of icy bodies that Neptune never settled into safe rhythms, worlds it merely flung, and it is still flinging them today. Every so often over the ages, Neptune's gravity catches one of these strays at the wrong moment and pitches it inward down toward the Sun, where it begins a long, unstable career wandering among the giant planets. Astronomers call these in-between objects centaurs, and they are comets in waiting. Handed inward from giant to giant, Jupiter eventually takes charge of many of them. and some end their journeys as the short-period comets that grace our skies on human timescales, tails unfurled, photographed by schoolchildren. Follow the family tree of many such comets backward, and you arrive at the cold nursery beyond Neptune, and at Neptune's own hand doing the throwing. Think about that the next time a comet is in the news. The dimmest planet, the one no eye can find, occasionally reaches into its frozen garden, picks a small world that has waited out there for 4 billion years, and tosses it sunward, where it blooms into a tail of light above our cities. Some of the most beautiful things that have ever appeared in Earth's sky were sent, in the deepest accounting, by Neptune. The planet even keeps companions in its own lane, sharing Neptune's orbit itself, drifting steadily around two gravitationally stable regions well ahead of and well behind the planet, rides a tribe of small bodies called Trojans. Quiet fellow travelers pinned in place by the combined pull of the Sun and Neptune, some of which have likely been circling in formation with the giant since the solar system was young. Neptune does not merely have moons and rings, it has an entourage strung along its entire orbit, an honor guard 4.5 billion miles around. There is one more encounter between Neptune and the Kuiper Belt worth telling, because humanity was the messenger. When the New Horizons spacecraft was launched toward Pluto in 2006, the fastest departure from Earth ever flown at the time, its route crossed Neptune's orbit on the way out. And by a coincidence so neat that the mission team made a small ceremony of it, New Horizons swept across the orbit of Neptune in August of 2014, 25 years to the day after Voyager 2's flyby of the planet itself. Neptune was nowhere nearby, of course, far around its long track, but the crossing was still a threshold. Past that line, spacecraft leave the realm of the giants and enter the realm Neptune governs from within. 11 months later, New Horizons reached Pluto and showed us Triton's sibling up close, glaciers of nitrogen, mountains of water ice, a heart of frost the size of Texas. And planetary scientists spent the following years comparing the two stolen twins, the one that stayed free in the belt and the one that Neptune took. Their surfaces echo each other so strongly that studying either one now means studying both. The prisoner and the free sibling compared at last, a century and a half after a brewer in Liverpool first saw the prisoner's light. Which brings us to the last thread of tonight, and in some ways, the most haunting one. Everything we have described, the storms, the arcs, the geysers, comes from that one brief visit in 1989, and a natural assumption would be that the Neptune in the photographs is simply Neptune, the way a portrait of a mountain stays true for 1,000 years. It is not so. Neptune does not hold still. We know because on the rare occasions we have looked back, the planet has been different every time. The first shock came just 5 years after the flyby. In 1994, astronomers turned the newly repaired Hubble Space Telescope toward Neptune, eager to check on the great dark spot, the Earth-sized storm that had been the flyby's crown jewel, the feature printed in every textbook and every poster, Neptune's answer to Jupiter's centuries-old Great Red Spot. It was gone, not shrunken, not drifted, not hiding around the far side. Gone. The largest storm on the planet, a vortex you could drop our entire world into, had dissolved back into the atmosphere without a witness, sometime in the 5 quiet years, while nobody was able to look closely. And before the astonishment had even settled, Hubble found a new dark storm, comparably vast, spinning in the planet's northern hemisphere, a storm that had been born, again, entirely unobserved. That pair of observations quietly rewrote what kind of world Neptune is. Jupiter's Great Red Spot has persisted for at least 200 years, likely more, a permanent landmark, practically geography. Neptune's great storms, we now understand, are mortal. They are born, they wander, and they die, on timescales of just a few years, faster than our visits, faster sometimes than our funding cycles. In the decades since, the space telescopes have caught the cycle again and again, a handful of great dark vortices rising and dissolving, each one the size of a world, none of them lasting. One recent northern storm was watched for the first time through most of a lifetime, seen drifting toward the equator where such storms are expected to shear apart and die, then inexplicably stalling, reversing and swinging back toward the pole as though it had changed its mind, shedding a fragment of itself along the way. The astronomers who reported it used the word astonishing in the formal literature, which is about as loudly as the formal literature ever speaks. And in 2023, for the first time, a great observatory on the ground in Chile managed to resolve one of these dark storms from the surface of the Earth across 2.8 billion miles, a feat of optics that would have sounded like fantasy to the Voyager team. Even the Webb telescope has joined the vigil now, and its first portrait of Neptune, released in 2022, showed the rings shining clear and complete for the first time in over 3 decades. The arcs and hoops that Voyager had to fly there to see, now legible from home. Our eyes have grown extraordinarily sharp, but an eye is not a visit, and every improvement in our vision has really delivered the same message. The message is that Neptune is alive with change, that its face is a weather report, not a portrait, and that we have been catching perhaps one frame of its film every few years and calling it knowledge. Even the planet's seasons have begun to misbehave on us. Neptune's southern hemisphere has been tipping toward the sun since before the flyby, a 40-year summer slowly ripening, and astronomers tracking the planet's temperature expected the sort of gradual, stately warming that a 40-year season implies. Instead, measurements through the 2000s and 2010s showed stretches where much of the planet cooled sharply in the span of a few years, followed by a sudden, rapid warming at the South Pole, swings far quicker than any seasonal clock should allow. It may be the chemistry of the high haze responding to the sun's own cycles. It may be something in the deep circulation we simply have not mapped. The honest summary, once again, is that the planet did something and we do not know why. Every time we improve our view of Neptune, it shows us a new behavior we cannot explain, which is either frustrating or wonderful depending on the kind of scientist you are. And I suspect at this hour of the night, you and I can agree it is wonderful. A world that still surprises us on every look is a world that is still, in the truest sense, unexplored. Will we ever go back? Here the story turns wistful, and I will not pretend otherwise. There is no shortage of desire. Within the community of planetary scientists, an ice giant mission has ranked among the loudest priorities for 2 decades, and the arguments are hard to answer. 2 of the 4 giant planets in our solar system have never had a dedicated mission, only a single shared flyby each. The most common size of planet in the galaxy appears to be the size we have studied least. Triton may hide an ocean. The twin paradox of the warm world and the cold world remains open. Proposals exist, worked out in detail, orbiters that would circle Neptune for years, the way earlier missions circled Jupiter and Saturn. Probes that would drop into the blue atmosphere and taste the furnace's breath directly, spacecraft that would skim Triton's plumes. Some have come achingly close to selection, passing round after round of review before losing, at the last table, to missions bound for nearer worlds. Distance is the whole problem. Neptune is so remote that a direct flight takes over a decade, even with a boost from Jupiter, and Jupiter is only in position to give that boost for a brief window every 12 or 13 years. Miss the window, wait a dozen more years for the map to come around again. Even in the most hopeful, realistic scenario, a mission approved in this decade, launched in the next when the planets allow, arriving in the 2040s or beyond. The gap between humanity's first close look at Neptune and its second will span more than half a century. Some of the engineers who flew Voyager 2 past Neptune will not see the second visit. Some of the scientists who will run that future orbiter had not been born at the first. 1 planet, 2 visits, and an entire human career fitting neatly in the silence between them. When people say the solar system is explored, that the age of discovery is over, I think of that gap. There is a world out there, 17 times the mass of Earth, with storms larger than our planet being born and dying unwatched right now, tonight, and the sum total of humanity's close acquaintance with it remains a single afternoon in 1989. And what of the one machine that made it there? This is worth knowing because the story did not end at Neptune. Voyager 2 never stopped. After Triton fell away behind it, the spacecraft kept flying down and out of the plane of the planets, and it has been flying ever since. In 2018, nearly 30 years after Neptune, it crossed the boundary where the sun's wind gives way to the thin breath between the stars, becoming only the second human object ever to enter interstellar space, its twin having crossed 6 years earlier along a different road, and it is still alive. As of this year, the machine that gave us every close portrait of Neptune is more than 12 billion miles from home, running on a power source that fades a little every year, its instruments switched off one by one to save warmth, like a house at the end of a long evening, turning out its lamps room by room. Its radio whisper, that 20-watt voice, now takes the better part of a day to reach us, and enormous dishes still turn to listen, and engineers, some of whom were not alive at the Neptune flyby, still send it commands written in a computer language older than they are. Sometime in the coming years, the last lamp will go out, and Voyager 2 will fall silent, but it will not stop. It needs nothing from us to keep going. It will pass in about 40,000 years through the outer fringes of another star's neighborhood, still carrying its golden record of Earth's sounds. And it will still be out there when Triton finally comes apart. The only object ever built by human hands that visited the last planet, outliving, in all likelihood, the civilization that flung it. If any part of tonight deserves to follow you into a dream, perhaps it is that. The little machine is still going. The visit never really ended. It just got very, very quiet. Now, as we finally come to the end of tonight's long drift, let us pull back and look at the whole of what we have seen, because Neptune, taken all together, tells one story, and it is a stranger and more beautiful story than any single fact in it. Every planet teaches a lesson. Mars teaches how worlds die. Jupiter teaches how worlds dominate. Neptune's lesson, I think, is that the universe does not owe our expectations anything, even at the bottom of the map, even in the dark where nothing should be happening. Consider the ledger one last time, gently. It is the dimmest planet, and it has the fiercest winds. It should be the coldest of the giants, and it pours out heat like a banked furnace. It should be frozen still, and it is the least still place the sun owns. Its twin should match it, and its twin is its opposite. Its great moon should orbit forward, and Triton swings backward, a stolen world with geysers on the coldest surface ever measured, falling with infinite patience toward the day it becomes a crown of rings. Its own rings should be even and eternal, and instead they are clumped and fraying, fences half fallen, changing between our glances. Even its storms refuse permanence, worlds within a world, born and gone between one photograph and the next. Nothing about Neptune is what it should be, and everything about Neptune obeys perfectly, laws deeper than our expectations, the same laws that let a man with a pen find it in the first place. That is the resolution of tonight's mystery, as much of one as science can yet give. The violence was never lawless. It was our sense of the rules that was too small, and the planet has been quietly teaching us better ones ever since, one hard-won glimpse at a time. They found it with arithmetic before any eye had knowingly seen it. They visited it once with a machine that spoke in 20 watts, and it repaid the visit with wonders. They watched its greatest storm vanish and new ones rise, and its seasons lurch and its rings fray. They keep discovering that it was stranger than the last thing they believed about it. That is the whole relationship between our species and the eighth planet, and it is barely 1 Neptune year old, 1 winter of acquaintance on a world of 40-year seasons. We have not begun. We have barely said hello. Thank you for spending this night out at the edge with me among the storms and the diamond rain and the slow backward falling of a stolen moon. If sleep has been circling you while we talked, let it land now. There is nothing more you need to hold on to. Every number tonight will still be true in the morning, and the ones that turn out to be wrong will be replaced by truer, stranger ones, which is the best promise science ever makes. And tomorrow night, if the sky where you are is clear, you might remember this. Out above your roof, in the dark between the visible stars, there is a point of light too faint for your eyes, as there has been every night of your life and every night of human history. It is deep blue, and hidden inside its blue there are winds that outrun sound, and under the winds it is raining diamonds, and around it a backward moon is falling, with 3 billion years still left to fall, and none of it, not 1 mile of it, can be seen from where you lie. The sky keeps its wildest things quiet. Neptune has never once been loud enough to wake anyone. Let it be the last thing you almost see tonight. The still point that is not still at all, keeping its storms to itself at the bottom of the sky. Sleep well, somewhere under the quietest, violent world there is. Good night.